Okay, so the next thing that we have over here is basically something called the factor theorem. And the factor theorem is kind of some sort of special case of the remainder theorem, meaning that in the remainder theorem we say that if p of x is any polynomial of degree of degree n greater than or equal to 1, and if a is any real number, okay, if p of x is divided by the linear polynomial x minus a, basically then the remainder of of p of x divided by x minus a is going to be equal to basically p of a. Okay, so that's basically what the remainder theorem is. Now there is another theorem that we can actually take from this theorem, and we can say that if p of x is a polynomial of degree n greater than or equal to 1, so we can say that if p of x is a polynomial, any polynomial of degree n greater than or equal to 1, and a is any real number, okay, then number one, x minus a is a factor of p of x. X minus a is a factor of p of x. If p of a is equal to 0, and number two is p of a is equal to 0. If x of a is a factor of p of x. If x minus a is a factor of p of x. Okay, so that's kind of something. I mean, that's actually the same thing, and this was basically called the remainder theorem. This is called the remainder theorem, and this theorem over here, this is called the factor theorem. The factor theorem, which is basically mainly based on the remainder theorem. So what that, and if you want to, it's easy to prove it's easy to prove the factor theorem over here. To prove the factor theorem, you can say that if so here in part 1 we said that x minus a is a factor of p of x if p of a is equal to 0. Okay, so then as the proof, for the proof, what you can say is that if p of a is here, the condition is that if p of a is equal to 0. So here I can say that if p of a is equal to 0, then p of x is going to be equal to basically x minus a x minus a times q of x. X minus a times q of x. Okay, so q of x is basically the quotient, and so basically you have a polynomial p of x of degree greater than or equal to 1, and a is any real number. Then we want to prove that basically x minus a is a factor of p of x if p of a is equal to 0. So now if p of a is equal to 0, then you can write p of x as x minus a times some quotient, and so p of a is equal to 0, and that is so because by the remainder theorem we said that the remainder is going to be equal to the remainder of a polynomial. If you divide your polynomial by x of a, then the remainder is going to be equal to p of a. Okay, so then of course you know that if you divide p of x by x minus a, the remainder is going to be equal to p of a based on remainder theorem. The remainder theorem. Okay. Now, if that is true, then I can write p of x is going to be equal to x minus a times some quotient q of x plus the remainder, and the remainder is going to be equal to based on this is going to be equal to p of a. Now here I'm saying that p of a is equal to 0. So if p of a is equal to 0, this becomes 0. So then p of x is going to be equal to x minus a times q of x, and that basically and this basically shows that x minus a is a factor of p of x. This shows that x minus a is a factor of p of x. And the reason why I'm saying this is that, well, of course you see that p of x is a product of x minus a and some other quotient. So of course any of these, either the x minus a or q of x, are both factors of p of x. So that's basically part 1. Now about part 2, we said that p of a is equal to 0 if x minus a is a factor of p of x. Okay, so if x minus a is a factor of p of x, then of course p of x is p of a is going to be equal to 0 based on the remainder theorem itself, because if basically the proof for part 2 is basically since x minus a is a factor of p of x, since x minus a is a factor of p of x, which is basically given here, okay, then p of x is going to be equal to, is going to be equal to some polynomial g of x, for example, times x minus a times g of x, and for some polynomial g of x, okay. So and you know that and you know that you have no remainder, because since you have since x minus a is a factor, then your remainder is going to be equal to 0. Okay, so now you have p of x is equal to x minus a times g of x. Now what I want to show here is that p of a is equal to 0. So now in this case, p of a is going to be equal to a minus a times g of x, and a minus a is equal to 0, so p of a is equal to 0, and that proves the second part of the factor theorem. So in short, what the factor theorem is actually saying is that if you have any polynomial p of x of degree equal to or greater than or equal to 1, and if a is any real number, then x minus a is a factor of p of x. If p of a is equal to 0, then x minus a is a factor, and if basically x minus a is a factor, then p of a is equal to 0. Both, and it works. Basically, it works both ways. Basically, these are actually converse. These are converse. What do you call it? Statements. I mean, this statement is the converse of this, and this statement is the converse of the other one. Okay. So far we have no problem here. Now, let me, actually I need to get a couple of things done, and I'll be back with you with the rest of this. We will go through some exercises, and we'll see where that takes us. Okay, so now as an example, let's say, for example, you have some polynomial. You have basically two polynomials over here. Let's say that you have x cubed plus 3x squared, okay, plus 5x plus 6, and you have another polynomial. You have 2x plus 4, and you want to know whether x plus 2 is a factor of this polynomial and also a factor of this polynomial. So basically what that means is that if you, based on any of those theorems, based on the factor theorem or the other theorem, what was that? The remainder theorem. If you divide this based on the remainder theorem, basically, if you have this polynomial here and this polynomial here, and if you divide this polynomial by this polynomial, then the remainder is going to be p of a. Okay, and a is basically something that you can calculate from this polynomial here. So then if you make a polynomial equation out of this, would be x plus 2 is equal to 0, and then x would be equal to negative 2. That means that your a is equal to negative 2. And now if you call this, for example, I don't know, p of x, and if you call this, for example, q of x, then if p of x is equal to, if p of a is equal to 0, then basically x plus 2 is a factor of, for example, p of x. And also if p of a is equal to, if q of a is equal to 0, then x plus 2 is a factor of q of x. Okay, so now you can simply check whether actually you can calculate the value of p of a here, meaning that meaning that P of A would be equal to P of negative 2, which is equal to negative 2 whole cube, plus 3 times negative 2 squared, plus 5 times negative 2, plus a 6, and that's equal to negative 8, plus 3 times 4, minus 10 plus 6, and that's equal to negative 8 plus 12, minus 10 plus 6, and that's equal to negative 18 plus 18, which is equal to 0. So since the remainder is 0, that means that x plus 2 is a factor of P of x. So that is the first part of the question. And then you can also check whether Q of A is equal to 0. So if Q of A is equal to Q of negative 2, which is equal to 2 times negative 2 plus 4, and that's equal to negative 4 plus 4, which is equal to 0. That means that Q of x is also a multiple of x plus 2, or x plus 2 is a factor of Q of x. Okay, so that is that. And there is also another good example that we can do before we get to factorization, and that is you want to find the value of k. Find k if x minus 1 is a factor of 4x cubed plus 3x squared minus 4x plus k. Okay, I call this, for example, P of x. So if x minus 1 is a factor of P of x, that means that based on the remainder theorem, or based on the factor theorem, P of basically 1 has to be equal to 0. And I'm getting the number 1 from here, meaning that x minus 1, if you set that to 0, x is equal to 1. So now P of 1 has to be equal to 0, because x minus 1 is a factor of this polynomial. Okay? So P of 1 over here would be equal to P of 1 is equal to 4 times 1 raised to the power 3 plus 3 times 1 raised to the power 2 minus 4 times 1 plus k is supposed to be equal to 0. And that is equal to 1 cube. 1 cube times 4 is equal to 4. That is 1 squared times 3 is equal to 3. That's a negative 4 plus k is equal to 0. So that's, these two will cancel out, and 3 plus k is equal to 0. So k is equal to negative 3. So that means that if k is equal to negative 3, then this polynomial will be a multiple of this polynomial, or this polynomial will be a factor of this polynomial. And now that we know basically a little bit about the factor theorem, now we know that about the factor theorem, we can actually use it in order to factorize some polynomials of degree 2 and 3. And the way that, and these are actually pretty useful and powerful things in mathematics. So basically the way that we used to factorize the second degree polynomials or quadratic polynomials. So let's say that you have a quadratic polynomial, and that is basically written in the form, let's say that it's p of x is equal to ax squared plus bx plus c. And if that's the case, you basically write this middle term in terms of, you have to split the middle term, meaning that, for example, you basically what you need to do, let me close this window, this is distracting me. Okay, so basically what you do here is basically what you usually do here, I mean what you call the technique here, what you do is that you basically write this middle term as sum of two terms. For example, you write b as, for example, m plus n, for example, in such a way that, meaning that m plus n, for example, is equal to b, and m times n is equal to a times c. Okay, and then based on that, then you will be able to factorize this whole polynomial here. As an example, let's say that you have, for example, something like x plus 3 times x minus 2, for example, something like this. If you multiply this, you'll get x squared minus 2x plus 3x minus 6, and that's equal to x squared plus x minus 6. Okay, now 3 minus 2 is equal to 1, x squared minus 2x plus 3x minus 6. Okay, so let's say that you have this polynomial here and you want to factorize it, and of course you don't know that the factors are basically x plus 3 and x minus 2. So in order to factorize this, you are looking for two numbers. For example, let's say a and b, such that a times b is the same thing as your coefficient here times your constant here, which is equal to 1 times negative 6, which is equal to negative 6, and a plus b is equal to your coefficient here, which is equal to 1. And it seems that, for example, it seems that 3 and 2 are the right numbers, so 2 and 3, for example. So if you write this as 3 minus 2 is equal to 1, and 3 times negative 2 is equal to negative 6. So then you can use these two numbers, in order to rewrite this polynomial, meaning that you write it as x squared minus 2x plus 3x minus 6. And then now you have the opportunity to, for example, take these two terms together and these two terms together. And from these two terms you can take out an x, meaning that here you have x minus 2. And from these two terms you can take out the 3, so 3 times x minus 2. And then from these two terms you can take out an x minus 2. And then that would be x plus 3. And then you will get your factors back. Okay, so that's basically something like a technique, some sort of technique that people actually do in order to factorize these quadratic polynomials. Now there is something here that but now let me actually tell you why this works. Okay. Now, the reason why that technique actually works is basically pretty simple. Meaning that, let's say that your second degree, your quadratic polynomial is, let's say it's x squared plus lx, for example, plus m. Okay, so this is a quadratic polynomial. And a quadratic polynomial is basically, you can write it as something like as the product of two factors, and these two factors are basically each a first degree polynomial. That's a safe assumption that we can make. So I can write it as x plus a and times x plus b, for example. So then in that case, for example, the roots of the roots of these or the zeros of this polynomial would be x1 is equal to negative a and x2 would be equal to negative b, for example, in that case. Now, if I assume that x squared plus lx plus m is my quadratic polynomial, and I want to write it and of course any sort of quadratic polynomial, you can write it in this form, x plus a times x plus b, meaning that it's the product of two linear polynomials. And so now if you multiply these two terms, these two expressions together, you'll get x squared plus bx plus ax plus ab. And then you can write this as x squared plus a plus b times x plus ab. So this is equal to x squared plus lx plus m. That means that if you can write two numbers, or basically two numbers a and b, such that a plus b is equal to the coefficient of the middle term, or L, and a times b is equal to the coefficient, is equal to the constant, or basically in this case m here, then you will be able to factorize your second degree or your quadratic polynomial. Now there is one more thing here that we need to discuss, and then we will get to some exercises. Okay, so the next thing that we have here, basically in the previous example that I showed you, basically we had some sort of polynomial where, if you paid attention to what we did here, I don't know if you had a problem. Where's the problem? If you pay attention to what we did here, the polynomial that we had here, in this polynomial the coefficient of x squared is 1. Okay, so this method of course works here. Now there are, and of course, since we derived this technique, if you want to call it a technique, since we derived this technique based on this situation, you might think that, for example, you might not be able to, or you might not be supposed to use it in a situation where where basically the coefficient of x squared is something other than 1 here. And in that case, you can also do some other experiment, meaning that let's say that you have another polynomial. Let's say that you have a quadratic polynomial ax squared plus bx plus c, and let's say that basically that you factorize this polynomial as, for example, something like px plus q times rx plus s, for example, something like that. So now if you multiply these together, you'll get prx squared plus psx psx plus qrx plus qs, and then you can add these two together, so you'll get prx squared plus ps plus qr times x plus qs, and then so as you can see, this is of course equal to ax squared plus bx plus c. That means that here your a is equal to pr, and your b is equal to ps plus qr, and b is equal to ps plus qr, and your c is equal to qs. Okay, so again you can see that your b is equal to ps plus qr, and 8 times c, and here basically 8 times c is equal to pr times qs. And but you can actually move these around based on the properties of I don't know, integers, real numbers, or whatever it was. We had this before. So based on the properties of numbers in multiplication, it's called the it's called the commutative property of multiplication. It's called the commutative property of multiplication. Excuse me. It's called the commutative property of multiplication. Okay, and what that's multiplication, and what that simply means is that basically you can write, for example, if you have a times b times c, you can write that as a times b, for example, times c, or you can move these around as in any way that you want. Okay, so based on this commutative property of multiplication, I can write this as PR times QS, so I can write this as PS times QR. So now in this whole situation, B basically in AX squared plus BX plus C, B is equal to PS plus QR, and A times C is equal to PS times QR. Basically the same kind of number, the same kind of configuration, meaning that PS plus QR and PS times QR, meaning that if you can find basically two numbers, and you can basically simplify this to, for example, PS is equal to some number m, and for example QR is equal to some number n, for example. Okay, so then based on this you can write that B is equal to m plus n, and A times C is equal to m times n, right? So that means that if you can write two numbers m and n in such a way that m plus n is equal to b, and m times n is equal to A times C, then you can still find you can still factorize this quadratic polynomial. Now let's do an example over here as well to see basically how this works. Oops, I need to get a new layer here. Okay, so as an example, for example, let's say you have 6x squared. I think there was something that I did here, but I don't. Okay, so let's say you have 6x squared plus 17x plus 5. 17x plus 5. Make this brush size 3 probably, and then around 40. And you want to factorize this polynomial. So let's see how you can do it. So again, you're looking for two numbers, for example, m and n, a and b, or whatever you want to call it, p and q, whatever you want to call it. You're looking for two numbers a and b, such that a times b is equal to 6 times 5, 6 times 5, which is equal to 30, and a plus b is equal to 17. Okay, so it's usually easier to start with the multiplication. So 30, you can write it as 1 times 30. You can write it as so 1 times 30, you can write it as 2 times 15, and I think 2 and 15 are going to work for us, meaning that 2 plus 15 is equal to 17, and 2 times 15 is equal to 30. So then I'm going to rewrite this this middle term as 2 and 15. So 6x squared plus 2x plus 15x plus 5. And then you can basically take these two terms together and take a 2x out. 2x times 3x plus 1 plus 5 times, for example, 3x plus 1. And then you can take the 3x plus 1 out. Okay, times 2x plus 5. And that's basically the factorized form of this polynomial. Or let's say that you have, let me see what this example is. Okay, so now there is one more way to solve this problem, and that is basically using the factor theorem. And then basically using the factor theorem, of course, it makes the solution much less straightforward, but sometimes it's actually useful, meaning that sometimes sometimes the situation is a little bit tricky, meaning that the numbers are a little bit tricky and there is no way for you to actually get the numbers like this very easily, like 2 and 15, and then put the numbers over here and factorize and get the factors. Sometimes you cannot do that. So when that happens, the factor theorem actually can be used in order to actually solve the problem. Now, what you can do here is that let's say that you have 6x squared. Let's say that you have 6x squared plus 17x plus 5, and you want to factorize it. Okay. So using the factor theorem, so of course you need to, what you can do is that you can take the 6 out. You can take the 6 out, and I'm going to tell you why you actually do that, because otherwise it's not actually possible to use the factor theorem. So if I take the 6 out, I will have 6 times x squared. We want to have a 1 over here, plus 17/6 x plus 5/6. Okay. So usually when you use the factor theorem, usually your original equation is in this form, something like this. And suppose that you have, for example, something like x squared plus 17/6 x plus 5/6, and you wanted to factorize this equation using the splitting method. You would have to be searching for two numbers, for example a and b, such that a times b is equal to, for example, 5/6, and a plus b is equal to 17/6. And of course it's not easy to find these two numbers. It's possible, but it's not easy. Okay, so in such cases you use the factor theorem. And And so I have taken, so now I have taken the 6 out so that I can actually use the factor theorem. And so you can, if this is equal to, let's say that this is equal to, let's say that this polynomial, let's call this p of x. So then this polynomial, oh sorry, basically let's call this polynomial, let's call this polynomial 6, let's call this polynomial p of x. So then this whole thing is going to be equal to 6p of x. Okay. Now let's suppose that the factors of p of x, or I'm sorry, the zeros basically, or this basically the zeros of p of x are basically, let's call them a and b. Okay, so therefore p of x would be equal to x squared plus 17 6x plus 5/6, which would be equal to x minus a, would be equal to x minus a times x minus b. Okay, so this would be x minus a times x minus b. Now now you know that this term over here, which is basically c in this polynomial, is actually equal to the product of the two zeros of the polynomial, meaning that if you have ax squared plus bx plus c and let me see, if I call this, for example, now the reason why I'm saying this is that if I take the zeros of this polynomial as a and b, so then this polynomial would be equal to x minus, I'm sorry, m and n, for example. Take the zeros of this polynomial as m and n, then you would have x minus m times x minus n, and this would be equal to x squared minus nx minus mx plus mn, and that would be equal to x squared minus m plus n times x plus mn. So here basically you see that the product of the zeros of the polynomial is actually equal to the constant over here, which is basically the same thing. So this is x squared, this is the coefficient of x here, which is b, and this is and this is actually the c, which is the constant over here. So this constant over here is actually the product of the two zeros of the polynomial. Okay, so then based on this, so then you know that a times b, which is the product of the zeros of the polynomial, is going to be equal to 5/6. Okay, and now you need to basically look for some possibilities for to look for two numbers whose product is 5, 6. For example, you could go for I don't know, you could go for there would be, of course, many different choices. You could go for example, 1/6, and you could go for example, that would be, for example, 5 times, or 5 times, for example, I don't know, you could go for 5/3 and 1/2. Okay, so you could go for 5/2 and 1/3. Okay, you could go for let me see what I'm doing here. And basically that's about it. So you would have these numbers, but then you see that the product of these numbers are actually is actually positive, meaning that both the numbers could be positive. When you add, when you multiply two positive numbers, you get a positive number, and also when you basically multiply two negative numbers, you get again a positive number. So then you would have to consider the positive and negative of all of these numbers. So then there's some possibilities for A and B, some possibilities for A and B. A and B would be basically plus or minus 1/2, plus or minus 1/3, plus or minus 5/2, and plus or minus 5/3. Okay, so that's basically all that you need here. So these are the possibilities for A and B. And now you can use the factor theorem in order to test whether any of these zeros are actually any of these numbers is actually a zero of this polynomial, meaning that if it's a zero of this polynomial, it is going to be basically based on the factor theorem. We said that if you have some polynomial, for example f of x, whose the degree is equal to, greater than or equal to x, and you have some real number a and some real number a, then if x minus a is basically a factor of p of x, then is a factor of p of x, then basically p of a is going to be equal to 0. And also if p of a is equal to 0, then if p of a is equal to 0, then what happens is that x minus a is going to be a factor of x minus a. I'm sorry, a factor of p of x. Okay, so what you need to do now is basically look for these. So basically right now the polynomial that I have over here is p of x, this polynomial over here, and I have these choices for basically for a and b, right? Now we said that if x minus a is a factor which I don't know, then p of a is going to be equal to 0. Okay, or so I'm not going to be able to use this part of the factor theorem, but I'm going to be able to use this part, meaning that the factor theorem tells me that if p of a is equal to 0, then x minus a is a factor of p of x. So now what I'm going to do is I'm going to test p of each of these numbers, and then if basically if any of them is equal to 0, then that means that x minus a is going to be a factor of the polynomial. So then you can start experimenting with these numbers. For example, let's say that you want to test, for example, 1/2. So, and 1/2 is actually plus or minus 1/2. Okay, it's actually plus or minus 1/2. So then you could calculate p of negative 1/2, which would be equal to negative 1/2 whole squared plus 17/6 times negative 1/2 plus 5/6. Okay, and that would be equal to 1/4, and that would be negative 17/12. That would be negative 17/12 plus 5/6, and that's going to be equal to 12. So that's a 3 minus 17 plus 10. So that's going to be equal to 13 minus 17, which is equal to negative 4/12, which is equal to negative 1/3. So clearly this is of course not a factor. I'm sorry, not a 0 of the polynomial. So in the same way, you can actually keep doing the same thing, and it's going to, of course, take you a long time in order to get to the factor. But now I don't want to waste any time over here, and I know that the factors are negative 1/3, negative 1/3, and negative 1/3 and 5/2. Okay, so you can actually test these two numbers over here. So for example, p of negative 1/3 is equal to negative 1/3 whole squared plus 17/6 times negative 1/3 plus 5/6. That's equal to positive 1/9 minus 17/18 plus 5/6. And then you can take the LCM as 18, so 2 minus 17, and then 3 times 5 is equal to 15. So that's equal to 15. 17 minus 15 is equal to 0 by 18, which is equal to 0. So negative 1/3 is basically one of your zeros. And then you can do the same thing over here for example, for 5/2. So for example, p of 5/2 is equal to 5/2 whole squared plus 17/6 times 5/2 plus 5/6, and that's equal to 25/4. And you have plus 5 times 17 is equal to, this is 12, and 5 times 17 is equal to 50, 85, 50, 35, 85 plus 5/6. And this is equal to 12. 3 times 25 is equal to 75 plus 85 plus 5. And there must be something wrong here. So 5/2 whole square plus 17/6 times 5/2. No, I'm sorry. Actually negative 5/2 is the number. Okay, I made a mistake over there. I read the factor, but I had to take the algebraic opposite of this number. And if you get this number, you get it to basically 150, 160, 165 by 12, which is basically clearly not what we're looking for. So I take it as negative 5/2, and then you can calculate p of negative 5/2. I apologize for this mistake. So then that's negative 5/2 whole squared plus 17/6 times negative 5/2 and times plus 5/6, okay? And then this is equal to 25/4 minus, that's 50 plus 85/12 plus 5/6, which is equal to 1275 minus 85 plus 5. Actually, that's a 10. That's a 10. And so that's the same thing as 85 minus 85 divided by 12, and that's equal to 0. So these two are your zeros, okay? Now you need to be careful here. These two are your zeros. So then, basically, based on the factor theorem, if p of a is equal to 0, which is basically clearly the case for these two numbers, now x minus a is going to be a factor of p of x. That means that based on this 0 now, the factor is going to be x minus a, and a is negative 1/3, so that's negative 1/3, and that is going to be the factor, which is equal to x plus 1/3. That's one factor. And again, based on this a, again the factor is going to be x minus 5/2, which is equal to x plus 5/2. Okay, so what that means is that you can write p of x as basically x plus 1/3 times x plus 5/2. Okay, that's your p of x. Now the polynomial that I had over here, was 6 times p of x. So that means that 6x squared plus 17x plus 5 is the same thing as 6 times this polynomial p of x. So this polynomial p of x is basically this thing. So this is equal to 6 times x plus 1/3 times x plus 5/2. And that is equal to, you have to multiply 6 by you can write your, for example, your 6, you can write it as, for example, 3 times 2, because if you do that, then you will be able to cancel out these two denominators here. So I write it as 2 times 3 times x plus 1/3 times x plus 5/2. Okay, and then what you can do is that you can multiply 3 by this thing over here and 2 by this thing over here, and so you would get basically 3x plus 1 3x plus 1 times 2x plus 5. And that's going to be equal to your polynomial. Otherwise, you could leave it like this as well if you want to, but well, it depends on what you want to do with your polynomial. And that's basically that. So we have a couple more examples here. We have a couple more examples here, so we will talk about them in the next video. I think they are going to take some time. I don't want to prolong this video more than this. I'll see you in the next video.